Good morning, everyone. I hope you're ready for a great day. And we start off with an invited speaker. I'm really happy to introduce Arun Kumar Singh, who's a professor of motion planning here at Tartu. And he did his postdocs in Singapore and Israel and Finland.
Yes.
And since 2019 is here leading a group that work now on many topics that you'll hear about, and also particularly using uncertainty in his work a lot. So without further ado, I'm happy to hand over to Arun, please.
Hello. Yeah. Thanks, Melis. Yeah, before I go to the main talk, I'll just start with some giving a short glimpse of what we do here in robotics in Tartu. Is this the one? Okay. So then I'll go to the main talk of the day. Okay. So here's my group. It's called Autonomous and Cooperative Systems. And cooperative is misspelled so that it aligns with my initials of the name. It was some trick that we thought of. At the moment, we have 5 PhDs, 2 research engineers, and 2 postdoc. Besides my group, also there are robotics faculties here who also have their own team. This is just my part of the lab. We work on a very diverse set of things, and it gives a short glimpse of what we do. So you see here some past work where we, you have to point here, right?
Yeah, you can point
on this side. Yeah. So here, a drone is following a human in a cluttered environment, and the drone is supposed to follow, keep the human in the field of view, avoid occlusions and collisions with the obstacle. We work a lot on the autonomous driving. Here you can see some of our works on how to drive aggressively, get safe in a dense traffic. A combination of RL plus model-based plannings on autonomous driving. This was one of the projects that we did during the COVID time on how to deploy mobile robots in human environments. So this robot used to carry test samples from one part of the hospital to another. And the key challenges here were that you have a very random environment and dynamic environment, and the robot needs to fulfill its task in that kind of settings. And this was one of the projects which we actually deployed in the field. So it was quite an interesting project. Currently we are doing a lot of bimanual manipulation. So here you'd see one of our recent works where we are developing this kind of some combination of learning and model-based reasoning on how to lift objects which are big, cannot be grasped by a single arm. So how to lift cooperatively, or how to hand over objects. Like if the one arm cannot reach that object, how to do this cooperative handover, and how to do all this in real time, so that you can adapt to. For example, here you can see a human is bringing some ball which acts as an obstacle, and the manipulator adapts to that in real time. So this is an example of off-road driving. This is one of our European projects where we are developing vehicles which can move on off-road conditions, not on-road. So it needs to move on uneven terrain and maintain stability. We're doing a lot of work on these drones where we have like a cooperative, like a swarm of drones, and how to coordinate them. And we do what we call as a learning to cooperate multiple robots, specifically here, in this case, drone. Yeah, this is one of the recent work which is also will feature in that talk. So I wanted to show the video up front. So this is in this video you see a drone which just has a onboard front-facing camera, just a monocular camera, and it needs to navigate, avoid obstacles with just an image, just a vision. So as you would know that like, when you navigate, depth is very important because that gives you the idea of geometry, where the obstacles are. So in this task, we wanted to do, can we do this kind of thing without depth sensing at all? Just with an image, a single image. We're planning to move robots through this kind of cluttered environment. And as you would see in the, when I go to the main talk, like the way we modeled it was a lot of uncertainty-based decision making. This was kind of foundation of this approach. And we were surprised by how well we could make it work. It was like we could actually get it to work on very sophisticated environments where you would actually need some kind of a depth sensing or a lidar to work. And it was working better than even like an end-to-end approach. Okay, I think this video played out before. How do you go back? Okay. Okay, anyways. So yeah, so this is a short glimpse of what we do. So now we'll go to the main part of the talk. Okay, so this is the main event. So how do you leverage predictive uncertainty for reliable model-based planning? There are three key things in this talk. So one is like, how does uncertainty feature in while you're doing robotic like motion planning for robots? Like, where can the uncertainty come from? Like in yesterday, you saw like a lot of the uncertainty in the computer vision tasks or classification tasks. Like in robotics, where does the uncertainty comes from? And it's slightly, the consequences are slightly different than, let's say, a vision task. And mostly I'll talk about this elliptic uncertainty and this one small work on epistemic also. So how does the uncertainty feature in? And if you have the uncertainty quantification in your problem, how do you leverage that quantification to do a robust downstream task of planning? It's like, how can you leverage the statistical information to make a more reliable planner? And finally, I'll talk about like how do you actually learn this uncertainty in what I call is a task-aware fashion. So like, and as I said, like the way uncertainty acts in robotics is slightly different from a typical machine learning task. And I'll show some motivation or my intuition on why the uncertainty learning aspect also has to change a bit. Okay, so the basic, let's start with some basic like notation. So there are currently two paradigms, broad paradigms on how do you do motion planning. So one is, if you can think of it as an end-to-end big neural network, which takes in perception and which can give you actuation commands. So this can be like a ChatGPT kind of a big neural network foundational model, which can do complex planning, and it's a big black box neural network, and that does everything. It will do the planning, it will do the execution, everything. The alternative paradigm is this model-based planning, where you actually have like some distinct components. So in all the key ingredients are shown here. So you have and let's say some kind of action policy. So this is some logic or some way of generating, let's say, actions for the robot. So basically, you think of it as some kind of a sampler from where you can sample a lot of action sequences. And there is some kind of a world model. Now, this world model can be a very broad term, but think of it here as a very specific kind of world model, which essentially takes your action and tells how the world will evolve over a future time horizon. Okay, so in particular, this talk will take a very specific case, which are very simplified world models, but generally this term is very loaded with, like, it can be very broad. So the actions goes into the world model, and what comes out of that is some state X. And you evaluate how good that state acts is through some cost function. You can also call it a reward function if you're doing from the reinforcement learning background. So this cost function takes in this x and tells how good the state acts is. And then what you do is you need some logic to update your action policy or how you generate action, some logic to update that so that you generate actions which leads to lower and lower cost. Okay? So this is essentially what model-based planning is. So you have an action, you roll out in the world, you see how good that is. If you're not satisfied with that, then you need some logic to improve your action so that the cost comes down. So essentially, in model-based planning, if you put it very in a nutshell, it's like a optimization problem. So you have a cost function C, which depends on X, which in turn depends on your action, and you have to minimize over U. So you can apply any optimization technique. For example, you can apply gradient descent to solve this problem. Okay. So this is in broad, in a very like basic manner, what model-based planning is. It's just an optimization problem, and if you fix with the world model function f and the cost function c from first principles like physics, then you would call this model-based planning, and you would publish in controls community, CDC like kind of conference or ICRA. And if you now start learning your world model iteratively, or even your cost function, then you can call it model-based reinforcement learning, and then you will submit to ICML or ICLR. So it just depends on the way you're approaching things. We can have different audiences for this kind of work. So let's take a concrete example. So let's say we have a setting where we want to we have an autonomous driving setting. We have an ego vehicle in green, and we have an obstacle in a neighboring vehicle, which you can think of it as an obstacle. And we want to plan for this ego vehicle. So in this case, you can think of it, your world model as consisting of a vehicle dynamics, which says how the ego is going to move if I apply some action, and some kind of a trajectory forecaster, which predicts how your neighboring vehicle, your obstacle, is going to move in future. Okay, so this can be your world model, a very simplified world model. And here, for the sake of simplicity, let's assume that the forecaster, the trajectory forecaster part, is what we are learning. So this comes from some data that we have collected, and we have fitted some neural network to it, and the forecaster part is what we learn. So, and the vehicle dynamics part is like we can just write it from the physics principles. So here, what we would need to do here is like we need some way of planning this ego vehicle motion so that there is very minimal collision risk. This can be one simple model-based planning task, that you plan a trajectory for the ego vehicle so that you minimize risk, and you have a forecaster as your inside a world model. You have a forecaster which can predict in a scene, given the maps and other kind of inputs, how neighboring vehicles are going to move. Similarly, I showed this monocular navigation task. So here you can, usually this kind of problems are done in an end-to-end manner. But we had a small intuition, and we brought some model-based reasoning into this. So we thought of this like, let's say you have this robot here, okay, and this is the robot view, and and this blue is, let's say, some trajectory or some action sequence that the robot can generate. Now, if you want to frame this monocular vision-based navigation as a model-based planning, the one way to do that would be that can I predict that if I take this particular action, whether I'm going to collide or not? Similar to autonomous driving setting, but here you just have like an image to do those reasoning. So here you have a trajectory from the robot's point of view. That trajectory in the physical space would look something like this. And the black line is, let's say, the worst case clearance that you can get. If the robot starts moving on this blue trajectory, the the black line is the worst case clearance that it can expect. Okay. Now, if you have actually depth sensing, you have LiDAR, then predicting the clearance would be a trivial task. You can just do with geometry. But here the trick is like, can we do it with just an image? And that's where some kind of prediction comes into play. So here, this world model can be something which can take an action sequence and predict what kind of obstacle, what kind of clearance the robot can expect from the obstacles, or what can be the worst case obstacle clearance. So that would be the part of the world model, and it would depend on the action, because what kind of action I take depends on how close I go to the obstacle. So that's an action-dependent world model, and then we do planning with that world model. And how we learn this will come later, but let's say suppose there is a model which can predict how close I can go to the obstacle given a set of action sequence. So then I can plan for this. I can plan a trajectory which leads to a lower collision risk. The one key question that, as I said, like how does uncertainty comes in? Like one key question that comes in is like whether your world model should be stochastic or deterministic. So let's say in case of autonomous driving, for example, let's say you have a neural network which predicts how the neighboring vehicles are going to move. So does that neural network should predict just one single trajectory, or it should predict like a distribution of trajectories or multiple trajectories? Okay. Now each has its own pros and cons. Like if you have a single trajectory, a deterministic prediction of your world model, what happens is that your planning problem becomes very simple. So if you if my x is a deterministic variable, if my world model evolves in a deterministic manner, then x is deterministic, then this becomes a regular optimization problem. But if x, the way the world evolves, if that becomes stochastic, like here in the second figure here, so here we have a obstacle, it can move in all this variety of possible ways. Okay. And typically we don't know exactly how it's going to move. We have some idea, and these are the different ways it can move. It can also move in some other ways not present here. Okay. So if you have some kind of the stochastic predictors, then your planning problem becomes very complex. Because if your x is a random variable, then your C function, cost function over a random variable also will be a random variable. Then this setting itself becomes a little bit or less well-defined, because what does it actually mean by minimizing a function over a random variable? So slight settings, like we need to change a bit how we do our planning, or the algorithmic aspect of that, to account for the stochastic predictors. Similarly, for this vision-based setting, we can whether your world model should predict just a one clearance, like okay, this would be the clearance from the obstacle if you execute the sequence, or it should predict like a bunch of different clearance that it can expect. Okay. Now, okay, one thing I forgot to talk here is that if you this. One advantage of the stochastic forecaster, why it is needed, is that you never know how your neighbors are going to move. So there is an inherent uncertainty that you can't get rid of. So you can go with a deterministic prediction. It will make your planning very easy, but it may not be of any much use, because there is an inherent uncertainty in the problem that it does not capture. And for example, if there's an intersection, you don't know whether your neighboring guy would move left or right, or if it's going to cut into your lane, or it's going to do a lane change, or it's going to overtake you. So there is inherent uncertainty in the problem that you can't get rid of. And that's why the current state of the art in forecasting is on stochastic forecasters. Similarly here, when you only see an image, you have no idea of the depth. You can do some guess of how the depth would look like. That goes into the realm of monocular depth estimation, which is also one of the tricks that we use here. So we can have some idea of what the depth is, but we can't know the true depth. So if you don't know the true depth, we can't exactly predict how the vehicle is, what would be the actual clearance from the obstacle if I execute a particular set of sequence. So here also, it makes more sense to consider your world model or your prediction to be a stochastic variable rather than a deterministic number. Okay, so these two examples were there to convince that, like, okay, how the uncertainty comes, and what's the need of that. Okay, and why wouldn't you go with like if you are actually learning a model, and lot of model-based reinforcement learning does work on just a deterministic transition model or a world model. So there is a very large amount of literature, but most of them are on the simulations, like they are trying to beat the benchmarks and all those things. But when you deploy it in real world, there is an inherent uncertainty that it can't get rid of. So it's better to design your network to handle those uncertainty rather than just forcing it to learn a deterministic network. Okay, so now, if you're convinced that, okay, we need some kind of a stochastic prediction, a stochastic world prediction, where you don't have a single answer of how the world is going to evolve, but rather we have multiple answers, then how do you leverage that information? So that's where the second part comes from. Where is the second pieces of information? Like so suppose there is uncertainty and you have multiple predictions, how do you actually leverage it? So again, let's go back to this example of autonomous driving. So you want to see if we can leverage uncertainty to minimize our collision risk. Okay. So for that, let's start with some notation. So let's say that we have some ego trajectory defined in terms of x of e, and we have this tau variable, which is an obstacle trajectory prediction, which is a random variable, and it belongs to some distribution p of tau, and that we don't know. So this would be your forecaster, your stochastic trajectory forecasting mechanism that you fit from the data. So you would learn p of tau from the data, but its characteristic or exact, like CDF or PDF, you may not be able to characterize. And so we have a random variable tau, and you can define some kind of function like f, which tells us that whether the ego and the obstacle footprints overlap, and that think of this function f of k as like that. And if it is less than 0, then the footprints don't overlap, and if it is greater than 0, then the footprints overlap. So you have this green rectangle here, you have a pink rectangle, and if this overlap, then this f becomes greater than 0. What exactly is this f is not that important. We can derive this from purely geometry. So if this overlap, then it becomes greater than 0. What you would want it to always be less than equal to 0. But since tau is a random variable, f of k will also be a random variable. Okay. Then you can define some kind of a worst case f, like this is f overlap over time horizon, like over multiple time steps k. This checks whether the ego and the neighboring vehicle or the obstacle is overlapping or not over a time, like space and time. So you can define some kind of a worst case f, which will be the max of this. And you can define a worst case collision violation as f less than equal to 0. So now, one way to do this probabilistic collision check or probabilistic reasoning is that suppose the probability that f is less than equal to 0 should be greater than some threshold that you define. So this probability that you overlap, that ego and the neighboring vehicle overlap. So p of whatever is inside that function here. So if this function, so what is the probability that this constraint gets satisfied? And we want that probability to be greater than some threshold eta. Okay. So if you specify, let's say you should not overlap with 0.9999 probability. Okay. Or you can also take a slightly relaxed setting where we can define the collision risk as this probability itself. Like what is the probability that I actually violate that condition? Okay, and we can call that as a collision risk. So what is the probability that my F is greater than 0? And F greater than 0, think of it as a condition that tells us that the ego and neighboring vehicle or the obstacle is overlapping in space and time. Okay. So what we want to do is we want to minimize this collision risk. So one kind of planning problem would be that can we compute some kind of a control sequence for the ego which minimizes this collision risk. Now the collision risk will depend upon this sequence U, because that decides how the ego is going to move, and that will decide whether it's going to collide or not. So plus there could be some other metrics also, cost less rewards you can put, but let's say the primary focus is that you want to minimize the collision risk, plus let's say keep one moving smoothly and not brake or accelerate too much. Those kind of things you can put. Now the core challenge here is how to compute this probability. As I said, if tau is a random variable, F is also a random variable. And if tau has a very complex probability distribution that you cannot characterize, let's say BDF, CDF, then F is also very complex. You can't actually compute this probability in any tractable manner. Now, one thing that if tau is a Gaussian, let's say, and F is affine, then this term here is pretty easy to compute. So probability you can compute if tau is a Gaussian, F is affine, then the overall expression also will be a Gaussian with some translated and rotated Gaussian, and then you can compute the probability of this P of this F can be easily computed. But typically we don't in a more general setting. That's as I said, like in a more general setting, the obstacle trajectory characterization would be some very complex distribution. And one of the reason is that like this P of tau usually is a neural network. So one of the very popular trajectory forecaster is this Trajectron++, very easy to use, and that's why one of the reasons it's popular. It can take maps and history and HD maps, so it can predict trajectories for all the agents in the scene. So it uses something like a conditional variational autoencoder to characterize the distribution of all the possible trajectories that that obstacle can take. Now, you cannot, but that is not very intractable to actually compute this P of F as a closed form formula or any optimizer-friendly formula, I would say. So what you have to do is you have to resort to what we call as a sampling process. So let's say we cannot characterize what P of tau is, but we have the ability to sample from it. So we can sample trajectories. So we can query as many trajectories as we want. Let's say we query 100 trajectories. Okay, and for each of them, we calculate how much our collision constraint gets violated. So it's kind of per sample collision violation. Okay. And then this F bar would be like that. So F bar would be some kind of a violation, some kind of estimate of like evaluation of whether if I take the jth trajectory sample from my probability distribution of predictions, whether that is violating the constraint and how much it is violating the constraint. Then one very common way of estimating the risk is to compute some kind of statistics over this F bar. And depending on what statistics you compute, you will get different kind of behaviors. So for example, you can do something called a sample average approximation and conditional value at risk. These are like the two of the most popular way of computing this kind of risk estimation or approximation of it. And very easy to implement and has some kind of intuitive understanding, meaning also. Like, and in 12 o'clock, we would have a talk. It's supposed to be given by my student, but I'll give that because he's not well, where we give one more way of computing this. So we give an alternative to this sample SAA and CVAR. We give one other way of estimating risk to samples, which outperforms both of this. But for this talk, I just kept it simple and like the standard way. So sample average would be just take how much the collision constraint is violated per sample, convert it into some kind of a binary indicator, 0 and 1, and just average it. So it kind of computes the frequency of violation of your collision constraint, and that kind of acts as a proxy for your collision risk. And CVAR would be slightly more complicated way of doing, slightly more involved way of doing estimating this, but the idea is essentially very similar. And it involves you have to compute what you call the quantile, or you have to compute this value at risk, which in turn involves computing this some kind of quantile statistics for this F bar. That means you have every trajectory obstacle prediction, you know how much it is violating or whether or not it is violating the collision constraint. You have those samples, numbers, and you compute some kind of CVAR or quantile over that, and that gives you this so-called CVAR estimate. And both of these work, and then these are essentially what your estimate of this probability of F is. And then you can plug back into your model-based planning or your optimization, and then you minimize over it. And that will give you some way of getting a trajectory with some minimum risk. So this is one way of handling uncertainty or task description, which depends on the uncertainty. In this case, the task description was to minimize collision risk. And usually when your task is defined in terms of as a function of some probability distribution, or let's say you want to minimize some cost function of some variable, the variable is random, then you have to actually reformulate or rewrite it into some kind of a deterministic way of, because you cannot do much with the function of a random variable. So you have to compute some kind of a deterministic surrogate, and this is two of the most popular and simpler ones to do. So no matter which statistics you use, either you use CVAR or EXAI, the main thing is sample. A good risk estimation seems to be sample efficiency. Key problem is how sample efficient it is. And in this case, in this kind of model-based planning, sample efficiency has a particular kind of meaning. So basically, you can sample from a trajectory forecaster. You can sample n number of trajectories, and then you can estimate risk using depth, either through EXAI or CVAR you do. And that will becomes your surrogate or your proxy for risk, let's say. Now, in the inference time, you draw 10 samples, you did a computation using that. Now, at the inference time, when the car is actually moving, it might see a sample which were not there during your computation. So it might see a very 11th sample from that distribution. And your risk estimation should be such that when you do this computation over these 10 samples, it generalizes to the unseen samples drawn from the distribution. So this would be some kind of a equivalent of what typical generalization is in conventional machine learning. You train on a particular data, and then it should generalize to unseen data from the same distribution. So this would be something similar to that. So you draw obstacle trajectories, you compute your estimated risk, but there could be something else in that distribution. You can't sample infinite amount from that. And each sampling or each query also costs. So you have to do it as less and less number of queries from your forecaster, and it should generalize to over the whole region. And that generalization depends on this risk, which technique you use. Whether you use the sample average or you CVAR, or as I said, we have our own custom technique which outperforms both of them. But nevertheless, the idea is it depends on what kind of approximation you use. And internally, what you've seen, it depends on the variance of your statistics. So you compute a risk based on 10 obstacle trajectory samples. Now, if you draw a new 10 samples, your risk will change. So, and then you keep doing this experiment over and over again. The variance of your risk estimate that decides how good your overall approximation is. So it has to do with this. So the lower the variance, the better the generalization would be. Okay, so I'll give a very small, a kind of toy example. So we have this a vehicle here, and in ego here. So this obstacle can cut into this lane, or it can keep on moving on this lane, or it can cut into the ego lane. And this is a toy example to show that like what happens if you don't take a probabilistic view of this planning, instead just think of forecasting also as a deterministic number, as a deterministic problem. So here you'd see, like, if you take stochastic, like if you do a distributional level reasoning, what kind of collision rates you can get. And if you do a deterministic reasoning, like if you just take forecasting one specific, like forecasting, trajectory forecasting, what kind of collision rates you can get. There are some more, later on I'll show it in other talk, some more complex example, but this is like a very simple. So essentially what we did here is, so there are multiple trajectories here. These are all samples from distribution, some unknown distribution. So we did a probabilistic way of this, whatever risk estimation that we did. And here, for the deterministic, we just took one sample out of the forecasting and thought of it as a deterministic number. And then we put that into the same planning algorithm, and then we computed what actually happens to the risk. And this is like some kind of validation of, like, you need some kind of probabilistic way of thinking, and although that's a more complex problem, needs more compute, but that's kind of inevitable. We can do the same thing with this monocular vision-based navigation task. So we have this clearance prediction, some kind of obstacle clearance prediction, drawn from some distribution which is learned from data. And if we assume that this distribution, this obstacle clearance prediction is a deterministic neural network, just like for, let's say, an MLP, we get some kind of 45% collision rate. And if you actually make it a stochastic entity, capture the aleatoric uncertainty, and then put that in your decision making, then you get like a 6% collision rate. And so you can welcome to check out this recent paper of ours, which is which handles this kind of where this problem comes from. Okay, so this was the like the second part of the talk. The third part, like now we saw that there is need to encounter or incorporate uncertainty, and how to leverage. So suppose you have uncertainty quantification of your problem, how to leverage that during your downstream planning. Now, the third part, how do you actually learn uncertainty? And yesterday we saw like this, a good insight, like how to decompose aleatoric or epistemic uncertainty. How does each of this come from the problem, from the sensors? So let's I would like to float this problem. What is the right uncertainty? Let's say a trajectory, take the problem of trajectory forecasting. What is the right uncertainty in a trajectory forecaster? So we can construct a very toy trajectory forecaster, let's say which takes in maps, past history, and it's just a Gaussian MLP, okay, and which models the trajectory of the forecasting or the obstacle trajectory as some Gaussian random variable. You have ground truth for all of this, so we can construct some kind of a negative log likelihood loss, and this would be some kind of a stochastic, very toy stochastic forecaster. So you can train it on the data, and in the inference time, you can sample multiple trajectories. So it fulfills that condition of being a stochastic predictor. And when you actually train this kind of models, you can get situations like this. Okay, so the predictions are good, like let's say in most of the cases very close to the ground truth, and the spread is very small. There's not so much variance. Okay. Now the key problem is we don't know whether this is actually the right uncertainty or right uncertainty forecasting, or it's some kind of under appreciation of the uncertainty. So because there is no supervision on the uncertainty, when you train this kind of models, all you get is the supervision is on the mean, and variance is kind of weakly supervised because you have to throw this NLL loss. There is no ground truth variance that we have to train this kind of models. And so we can have situations where there is actually no variance. You can also have like an opposite situation where we can have a very large spread, okay, unreasonably large spread. And interestingly, if you look at the trajectory forecasting literature, the metric that they use is called this best of K metric. Essentially, I have a bunch of black trajectories here, which are like the predictions from this Gaussian ML, let's say a Gaussian MLP. And I will compute all of this residual of all these predictions from the ground truth trajectory, and then I will report my best performing sample. This is called the best of K prediction. And if you look at the trajectory forecasting papers, these are like that's a go-to metric. They'll only show this best of K, and whoever's best of K is 0.1 better, that is the next SOTA, and the next month new SOTA will come. So, but one thing that they don't do is like they don't show how is their forecasting actually affecting the planning, or whether it's affecting the planning in a good in the right way. So like if you have like a very constant, very low variance, whether that's good for the planning, downstream planning, or you have a very large spread, both of them can give you exactly the same best of K prediction, but which of them is good or bad, that's kind of a very tricky question and kind of an open-ended question. So which one it should be? So, so my hypothesis is that like your uncertainty in robotics or in kind of planning decision-making problems, your uncertainty, good or bad, or how it affects, is all decided by your downstream task. Your uncertainty doesn't live in a vacuum. So your uncertainty depends on what your task is. So my first postdoc was in a neuroscience lab, where I was trying to use this kind of things to write predictions how the human arm will move. So there was a very famous experiment. Like, suppose you have to, let's say you have a ball and you want to throw it onto the wall, and your task, and human arm is supposed to be a stochastic dynamics model. That's like a well-established fact with some noise characteristics that you can learn. So suppose you have to have a ball and you want to throw it on the wall, and the task is it should just hit the wall as fast as possible. So if you do this experiment multiple times, you'll see that there is a huge spread over where the ball hits the wall. Okay, because that's not the task. The task is it should hit. So there is a huge variance over where the ball will hit, because that's like the task irrelevant uncertainty. You don't care about that task. Okay, so if you couple uncertainty with the downstream task, there would be something like a task relevant uncertainty that actually affects your task, and that actually should be captured by your world model, your forecaster. Task irrelevant uncertainty may not be that important, and you can just let go of it, and you can focus more on the task relevant part. So one way of doing that is you don't train forecaster alone. You train forecaster with the downstream task. So a conceptual model, like something similar we have also used in our work, is that let's say we have the same Gaussian MLP forecaster. We have this NLL loss that supervises my mean prediction and my variance also. Now during training time itself, I can sample from this current mean and variance. You can use this reparameterization trick, that from this mean and variance, I can get my obstacle trajectory samples. And that goes into my model-based planner, okay? And I get my optimal solution out of that, and that is compared with what is my ground truth optimal solution. So your forecaster is, so your forecasting problem, you have a data set for the forecasting problem and also for your planning problem. Often both comes in the same data set. You just need to just say that, okay, this is my solution, this is my problem. So you have a supervision on the actual optimal planning decision or optimal control, and then you just backpropagate through end-to-end. So your loss, so your this kind of what you call it, the planning loss, or this will kind of supervise what your variance should look like. Okay. If the variance is very high, your planning would produce a decision which looks very different from your recorded optimal solution. So this kind of creates like a very strong supervision on training variance or training uncertainty, and that supervision comes from the downstream task. By the way, this does not only happen if you're training like a toy Gaussian MLP model. Like if you can even put a very high sophisticated flow matching, and you kind of face the same problem. I think it's a very common problem, well-known problem, that something called as variance collapse in flow matching. So where if you're doing image generation and you sample from flow matching, then you'll only get a similar set of images. So the variance is already collapsed. So you can get similar kind of variance collapse or variance exaggeration, whatever. Both of them can, even if you instead of Gaussian MLP, you can put a more sophisticated generative model. So this way of training provides some strong supervision on the variance signal and gives you a proper calibrated, or calibrated is a strong word, like uncertainty which is useful for your task. So it assumes that we have a ground truth solution, a ground truth control. So the right variance is one that results in control used as close to the ground truth. We can train this end-to-end, but this is sufficiently more difficult to train this kind of network because of this layer. So if you want to backpropagate from this last block back to here, you have to backpropagate through this argmin operator. So you have to backpropagate through this optimization routine. And it's called, you have to use something called as implicit differentiation. On paper, it's not that complex. And there are some libraries to make it work, or how to differentiate through optimization solvers or optimization layers. Theoretically, it works. Like it's very easy. But the moment you put on training, you start getting Cholesky decomposition error, and then your work stops there. So there are some ways, like some nuances on how to train this kind of networks with this kind of implicit layers in a reliable fashion. So there is some kind of a workload or some extra bit of effort is needed to make this kind of network train. Okay. So one example of this is an algorithm called diff stack, which came from NVIDIA. They do something similar to what I've shown. Maybe just the architecture is more complex. They don't use Gaussian MLP. They have a conditional variational autoencoder followed by a planner, and then they backpropagate. They do the end-to-end training for all of this. So this is called diff stack, short for differentiable stack, end-to-end differentiable stack. So, and this was one of the like a very interesting result that this shows. So here, all the blacks are the agents in the scene. So they just take one of the agents as the ego, and they try to forecast its motion. So in this case, in the first figure, so this is the black, actually the ground truth, and the red is what their planner is predicting. Okay. So if you do a standard way of doing, if you train the forecaster first, and then you do the planning, so what happens is that you can get your forecaster can be good in average sense, but can have a very huge spread. Okay, this is what I was referring to. And your planner can then produce a trajectory which is very far away, which tells you that you have to deviate from that to avoid collision. And that is very different from what the actual ground truth trajectory is. And what they show is, like, when you have do this end-to-end training, here the spread is much. Here also the spread is much, but the most of the samples are concentrated in the middle towards this. So the more confidence region is concentrated around this, like the original prediction. And then we get a less deviation on the planar trajectory, which is like closer to the ground truth. So here, if you just do, like forecasting, if you just train for forecasting, the uncertainty that you will get is what you get, like depending on where you converge in the local minima space. So you can get a variance collapse, you can get this kind of thing also, depending on where your parameters take you, because there is no supervision on what the variance. And this kind of end-to-end training will kind of make you supervise the variance based on your downstream task, and give you very reliable results. We actually implemented this exact same idea for our monocular vision-based task. So we had two obstacle clearance predictor. One was just a simple Gaussian MLP, and where we, during training, we use a LiDAR to collect the ground truth clearance, and then we try to reconstruct the ground clearance just based on image. And our basic model was just to use the Gaussian MLP, and this is what we tried. Didn't work that well. And then we went back to the drawing board, and then we did something like this, where our obstacle clearance predictor has this NLL loss, but then we also see that what kind of predictions are coming from the current mean and variance, and what would be my risk. And I have some kind of a ground truth risk based on my LiDAR measurements. So I have some privileged information during training that if my trajectory is this, I don't collide, so my risk is 0. And if the LiDAR measurement says that the trajectory is going to collide, that my risk is 1. So what the network is predicting as the clearance, or the distribution of clearance, that should lead to the same kind of risk, or similar kind of risk as my ground truth risk. And so we have a kind of a cross entropy loss over the binary cross entropy loss over the risk head also. And this led to a very model which was performing very well. It had all the right distributional metrics, like lower energy score, even the residuals were lower, and like eventually all that translated into like a lower collision rate also. So the baseline model was 28%, and with the task-aware training, we got like 6.6, the best performing model. Yeah, I'm towards the end, so there's a small work on. We are also, so all of this was on aleatoric uncertainty because the NLS were there for that. We have this epistemic uncertainty. So one of the things that we are doing is off-road navigation. So we see from LiDAR some part of the terrain. We don't see some part of the terrain because there is an occlusion from the terrain itself. So how do you guide your paths to be to the known region and not to the unknown region? So the one way we do is that we reconstruct the terrain using the known information, like observed point clouds. And then we do this Laplacian approximation of this epistemic uncertainty of the regression model. And that gives us some idea of where the terrain uncertainty is. And then we guide the trajectory towards more observed regions through that. Okay, so concluding. So uncertainty is important in reliable world retrieval setting. You need more compute. You need more more sophisticated algorithms to leverage uncertainty. And you have to model this task uncertainty in some kind of a clever manner, which is aware of how that is being leveraged by the downstream task. Finally, to conclude, these funding agencies, these are what made this work possible. Most of this work is from thesis of my student who soon graduate, Basan. And yeah, that's it.
Thank you for the great presentation. I have many questions, but
yeah.
I guess the first one is, it's interesting to see you says like for the model-based planning, you also reached the conclusion that you need to do it end-to-end. But then my question is, like, let's say from autonomous driving, we are already using end-to-end models.
Yeah.
Like, have you compared with these models?
So this end-to-end is slightly different from that end-to-end. So this end-to-end, what I call is this like these modular end-to-end stack. So each component, so you have a forecaster, you have a planner, you have a controller. These are all differentiable. These are all different stacks. They can have neural network as a part of it. They are trained end-to-end, but these are all different blocks, each grounded in their own like some kind of a physics-based reasoning. So for example, this forecasting model could have some kind of physics-based kinematics, dynamics constraints, and all those things. So it's kind of the middle ground that, at least in our lab, that's what we are trying to do. So in a typical end-to-end, we'd have one big neural network, like a transformer model. This would be a modular end-to-end, where we have different blocks, but still you have the capability to train this end-to-end. And so that you don't observe what you call as an objective mismatch. You don't train one component without knowing how it's going to affect the downstream component.
Okay, thank you. But I mean, do you see, my question is more like, do you see the benefit of doing this, like, kind of hybrid of model and end-to-end?
I mean, we did compare, for this vision-based navigation, we did compare with end-to-end. Like so there are like a couple of vision transformer-based, so-called foundational model-based approach, and those didn't. So they worked really well on sparse environments, but on realistic, more cluttered environments, they never went past 20%. And that's very obvious because it's neural networks are not good at constraint satisfaction. So like you're sampling from an unconstrained model. The probability that it will satisfy a constraint is pretty low. Okay, it depends on the feasible space also. So end-to-end models are not good for that. So vision-based navigation talks explicitly compared end-to-end within our approach. This kind of a hybrid model-based end-to-end mixture approach.
Yeah, I have just one more question. Like, because in your second part of your talk, you are assuming the trajectory forecaster are based on sampling.
Yeah.
But on the third part, you says this is a Gaussian MLP, and yeah, we don't care about the variance. We just care about the planning performance. Like
no, I mean the Gaussian MLP was like a toy example because I could actually say what the variance is. I could, but that need not be a Gaussian MLP. You can put anything there. So Gaussian MLP was like a toy example that I concluded. So it need not be. You can put flow matching or diffusion there. That doesn't matter. The variance collapse or variance aggregation exploration will come there. It can come either of the cases, even if you put diffusion there.
Yeah, my question is like, there are some models like predict like Laplace mixture,
yes,
and someone use diffusion or this sampling-based method. Which one do you find is best?
Okay, so that will be decided by your task. So that's the open question. Like we don't know. So just based on forecasting metrics, you can't say which one will be better.
We can take a bit more time for questions, so if you have any, but I have a question. So I think it's very interesting, like you put together this prediction with uncertainty together with planning into one holistic model that you're training end to end. But your loss function eventually with which you train is only about the task as a whole, right? Or do you have intermediate loss also on the uncertainty side?
We have intermediate loss. Like for example, if you take like a Gaussian MLP, the NLL loss, you have supervision over the mean. So you have the ground truth information about what you're forecasting, the mean. Variance, not so much, and that's what the idea is. Like variance will come from the task, mean will come from there, so you have supervision at both places. You can do without the supervision also. That's like also like my intuition is that it may work, because let's say there are two humans which are trying to avoid each other. They might not do an exact trajectory forecasting. They might be driven by just more like general intent on where they are going and the way they adapt their planning. So maybe you can train it without the intermediate loss. At the moment, we do use intermediate loss, yes.
But in the intermediate loss, you only aim to match the mean, and so something like MSE loss or something like that, and not something like NLL or with probabilistic evaluation.
No, we can use, we have used NLL, and the main problem is that NLL, the variance just collapses. So if you just put a lower bound, it will just go to the lower bound. And if your model is very like high capacity, it'll minimize the mean, and the variance can go to a very small value, which may not be descriptive of the problem. Or it can happen the other way also. Variance could be very big, and that can lead to different kind of behaviors. So the intuition is that the variance supervision will come from the task.
So I think there is broader implications also for potentially other fields where people are trying to do prediction with uncertainty together with a downstream task. And I mean, if you train it, let's say end to end, there is a risk that I mean, maybe your uncertainty part actually, I don't know, maybe it's no longer a valid, really valid probabilistic uncertainty estimator, but maybe it's okay as long as your overall performance improves. But maybe maybe we're missing something, and we can do even better if we will also align the predictions better. Maybe there is more to be gained.
Yeah, exactly. That could be there. I mean, this is like a very easy, a robotics way of handling that problem of like mismatch between the uncertainty. There could be, there could be certainly a better way of like having a good intermediate loss. But at the moment, I don't have a very good answer for that. So my intuition is that it will just come from the task. Yeah.
Okay. Thank you very much.
Yeah.
Maybe just a few words about this as well. This is a Dubai chocolate with words or letters Wummel 2026 written on here. This is Laura's special. She made it Dubai chocolate. Yeah, please enjoy. Thank you. This tag as well.